when you connect to Wi-Fi, when your phone backs up to the cloud, when your hard drive encrypts itself, the same algorithm is doing the work. AES, the Advanced Encryption Standard, it's the most deployed encryption algorithm on Earth today. And it's running right now on the device that you're using to watch this video. AES is a symmetric block cipher. 3 words doing real work. Symmetric, the same key encrypts and decrypts. Block cipher, it operates on fixed size chunks of data, exactly 128 bits per block. And by cipher, we mean a specific mathematical algorithm that transforms readable data into scrambled output. In 1997, NIST, the U.S. National Institute of Standards and Technology, announced an open competition. The previous standard, DES, had a 56-bit key that was too short for modern computing. It was brute forced publicly in 1998. NIST wanted a successor that would last decades. 21 algorithms were submitted. 15 were accepted as candidates. After years of public cryptanalyses, the field narrowed to 5 finalists: Mars, RC6, Rinjdale, Serpent, and Twofish. In October 2000, NIST selected Rinjdale, designed by 2 Belgian cryptographers, Joan Damon and Vincent Rijman. AES was published as Federal Information Processing Standard 197 in November 2001. The standard received a minor editorial update in 2023, but the algorithm has not changed since. AES has 3 variants: AES-128, AES-192, and AES-256. The number is the key length in bits. The block size is always 128 bits, regardless of which variant you pick. Longer keys mean more internal rounds of processing. 10 main rounds for AES-128, 12 for AES-192, and 14 for AES-256, plus a pre-round key addition with the final round structured slightly differently. More rounds, more security, slightly slower performance. For most modern systems, the performance difference is negligible because of hardware acceleration. AES is what cryptographers call a substitution permutation network. Each round of AES applies 4 transformations to the 128-bit block, treated as a 4x4 grid of bytes. Subbyte substitutes each byte using a fixed lookup table called the S-box. Shift rows rotates the rows of the grid. Mix column scrambles the columns using finite field arithmetic. Add round key XORs in a round specific key derived from the original key by a process called the key schedule. Repeat that pattern 10, 12, or 14 times, depending on the variant, with the final round omitting mixed columns, and you have AES. The 4 operations don't matter to most people who use AES. What matters is what they accomplish: diffusion and confusion, the 2 properties Claude Shannon identified in 1949 as the foundation of secure cipher design. Confusion means each bit of ciphertext depends on many bits of the key in complex ways. Diffusion means changing 1 bit of plain text changes roughly half of the bits of ciphertext. AES achieves both with mathematical thoroughness. But here's the thing that we don't talk about a lot when they say AES encrypts your data. Raw AES doesn't. Raw AES only encrypts 128-bit block at a time. To encrypt anything larger, a web page, a file, a stream, you need a mode of operation. The mode defines how AES gets applied repeatedly to handle data of arbitrary length. And the choice of mode matters more than the choice of key size. There are 4 modes you should know. ECB, Electronic Codebook, the simplest mode. Each block is encrypted independently with the same key. ECB is insecure by design for any data with patterns. Encrypting a bitmap of Tux the Linux mascot in ECB mode produces ciphertext that still looks like a penguin. Patterns survive. Never use ECB for anything except encrypting a single block of random data. CBC, cipher block chaining. Each plaintext block gets XORed with the previous cipher block before encryption. CBC was the dominant mode for TLS, IPsec, and SSH for decades, but CBC by itself doesn't authenticate the ciphertext, and the broader CBC-based design in the pre-1.3 TLS led to a series of devastating attacks. Beast, Poodle, Lucky 13. The lesson is this: encryption without authentication is a vulnerability, not a defense. Then we have CTR, counter mode. This turns the block cipher into a stream cipher by encrypting an incrementing counter and XORing the result with plain text. CTR parallelizes well, which is good for performance, but like CBC, it provides no authentication on its own. GCM, Galois counter mode, which is the modern default. GCM combines CTR mode encryption with a built-in authentication tag using Galois field multiplication. It's what cryptographers call an AEAD construction, authenticated encryption with associated data. AEAD means encryption and authentication are inseparable, which prevents the entire class of attacks that plagued CBC. AES-GCM is the standard cipher suite in TLS 1.3 and the dominant authenticated encryption mode on the internet today. It's the answer. One critical caveat about GCM, though. The initialization vector, the IV, must never repeat for the same key. IV reuse in GCM is catastrophic. It allows attackers to forge authentication tags and recover the key stream. Every well-implemented AES-GCM library handles IV uniqueness automatically. Every poorly implemented one does not. So let's talk about why AES is fast. Modern Intel and AMD processors include dedicated AES instructions called AES-NI. ARM processors have equivalent crypto extensions. These instructions execute the entire AES round in hardware. The result is encryption speeds measured in gigabytes per second on a single core. Without hardware acceleration, AES is several times slower. With it, AES is essentially free, fast enough that there's no practical reason to use weaker encryption to save CPU time. This is also why AES-256 isn't meaningfully slower than AES-128 on modern hardware. The extra rounds add maybe 20% overhead, which AES-NI absorbs without breaking a sweat. Now, the question on every cryptographer's mind in 2026 is AES quantum safe? There is a quantum algorithm called Grover's algorithm that speeds up brute force key search. Grover provides a quadratic speedup, meaning a quantum computer would only need the square root of the time to brute force an AES key. And that sounds bad. The textbook conclusion is that AES-128's effective security drops from 128 bits to 64 bits against a quantum attacker. And AES-256 drops from 256 to 128. The reality is more assuring, though. Grover's algorithm cannot be parallelized in any meaningful way. The speedup only applies to a single sequential thread of computation. NIST analysis and the consensus of working cryptographers is that AES-128 remains practically secure even against future quantum computers. AES-256 is the firmly post-quantum safe by any reasonable definition. You don't need to migrate AES to defend against quantum threats. You only need to migrate the asymmetric algorithms, RSA, classical Diffie-Hellman, ECDSA, which Shor's algorithm actually breaks. So the picture is this: AES is a 25-year-old algorithm that has survived a quarter century of cryptanalysis without a single practical break. It runs at hardware speed on every modern device. It defends most of the encrypted traffic on the internet. It is post-quantum safe, and it almost certainly is the algorithm protecting whatever sensitive data you have currently stored on the device where you're watching this video.